So as John said, my name is Sean Kane. I'm from New Relic. I'm the site engineering manager for our infrastructure team. We are largely responsible basically for everything from the network up through the OS and all the hardware that that involves. So today I'm going to be talking about automated hardware provisioning in the real world, or I like to say how to build your cloud out of metal. So a lot during this conference, we've been hearing people talk about alerting and monitoring and sort of what do we do in operations when everything breaks. And I want to take a step back and actually talk about how do we set up everything that then is later going to break and page us endlessly. And you know, a lot of us are dealing with basically cloud technology, and we've sort of abstracted away all of the things that we have to deal with that actually support this. And even in the best OpenStack implementation in our offices, somebody somewhere is having to make sure that there's actually hardware in racks connected to our network that's giving us all this higher level functionality. So basically, where are we trying to start, or where are we starting from, and where are we going to end up getting to? New Relic, about a year and a half ago, was basically in a position where they were largely making very small hardware orders, just a handful of servers at a time. We'd have a new service that was coming up. We'd buy the 6 servers we needed for it. Somebody who was remote hands would go in, put it into a rack, set it up, probably PXE boot it by hand, or maybe we would come in on the remote management console and via KVM PXE boot it. And then we would have something like Cobbler set up that would allow the system to install and then run Puppet. But then we basically had a new project that was about to launch, which is actually since then has now launched, Insights. And we had a need to be able to bring up mini racks of servers very, very quickly, approximately 120 systems, about 4 racks, and do this really within a week's time frame. We had a couple of months that we knew this was happening. And so we wanted to build a system that would allow us to basically bootstrap all of this. So outside of having somebody actually install these systems into the racks, the rest of the process could be automated. So this is basically the process that we came up with, the steps that we needed to do. Don't spend too much time trying to read this eye chart. I will break it out as we go forward. But in this sort of hub and spoke, each of these spokes is basically one significant part of the process. And then the center is some sort of data store, something that allows you to track your inventory, what servers you have, what state they're in, the history of any repairs that might have happened on them. And again, I'll go into that in a little more detail here. So what did we want to do? We wanted to design something that allowed us to stay agile. This was a really big, important piece for us. There's a lot of tools out there that try to solve this problem in really big ways, but sometimes they're problems in and of themselves because they force you down a path, a decision that somebody else has made about how you should be doing this. And we wanted to make sure that basically we designed something that used just enough process. So the process was only there where it had to be, and it would be really easy to modify and change later. So the bare minimum things that we needed to do was we needed to be able to detect that there was actually hardware in the rack. We needed to be able to inventory it so that we had details about all the hardware that was there, test it, make sure it was actually working as expected, and then of course install and configure it so we could hand it off to our developers. So first I want to go over some lingo. There's a lot of names of standards and a few other things that I'm going to use in this talk. And I don't know, obviously, how much individuals in the audience know about this stuff, so I'm going to go over a few of these. So the first one is IPMI. This is a standard, it means Intelligent Power Management Interface. It's built into almost all modern server hardware. And it does a few pretty low-level things. Mostly it's intended to be able to do something as simple as turn the server on, turn it off, reset it on command. As long as the server's plugged in, it's got some source of power, we want to be able to do these really basic functionalities. It also allows us to query and tune some of the sensors, the hardware sensors within the devices. It allows us to get some inventory about what's in the system, allows us to access hardware logs, and finally can do some basic SNMP or SNMP traps to tell you if something like a CPU temperature threshold has been passed. The baseboard management controller, I mostly bring this up. It's not really critical in the sense of needing to know about it, but you'll hear a lot of people use this term, and it's confusing to a lot of people. This is basically a chip. It is sort of the heart of the IPMI and is really the minimum management component you need to do a lot of this work. And the other big thing is the remote management card. And anyone who's in ops, this is something that you're really familiar with. And unfortunately, it's also the one area where there really is almost no standardization. So Dell has their DRACs, HP has ILOs, IBM calls them RSAs. And these tools, though, are the things that allow us to basically manage our servers at all times. And they're also allow us to do some of the deep management into our servers, things that are particular to the brand of servers we buy. So they'll allow us on our Dell to deal with the Dell firmware. It brings in a lot of deep system capabilities. It usually knows all the details about that vendor, the type of hardware they use, and can give you really detailed inventories. It also provides your console over IP, so that if you're remote, as most of us are from a lot of our hardware, this is the way that you can see the console even when you're halfway across the country. And these usually provide SSH and web interfaces to allow you to access this information. So this is what the IPMI sort of breakout looks like. Basically at the top, very top center there is the remote management card. This is typically how we'll access all the functionality that's inside here. You see the base management controller, this BMC is right in the middle. And then there's a couple of red lines on here, and these are various ways to talk to the system. You can do it over the LAN, you can do it over serial or modem interface. And then finally, there's a system interface. So if you actually have an OS installed on the system already, you can also run commands at the Linux shell that will also allow you to access all this information and do things like restart the system. And then finally, I want to talk about the CMDB or DCIM. These are sort of industry terms, but largely they mean the same thing. This is your sort of system of record, your source of truth about what hardware you have installed, any history that's related to that hardware, its current state, things along these lines. And this is sort of going to become the heart of the system that we're talking about, the place that you track the current state of your hardware. So the first step that we need to do is basically order and rack the hardware. And this is an important step because really the very first thing that we'll need to be able to do is make sure that our remote management cards will actually DHCP by default when they're plugged in. And amazingly, this actually is not the standard on a lot of servers, either for security reasons or various other reasons. A lot of times they are actually set with some sort of private IP address, like a 192 address space. And so you have to ask your vendors to set their RMCs to be DHCP. Most vendors will do this. Dell does this for us, so we get them set up correctly right out of the factory. And then the other thing that you can do too is also have dynamic DNS set up. Some RMCs will also allow you to do that, so that when the remote management card comes up, it'll actually have an address applied to it. Could be like iDRAC dash a serial number at your domain, and that way they're also easy to find. So now we have to bootstrap the system. So basically, this is what this process looks like. The RMC is gonna make a DHCP request to our DHCP server. We're gonna put some information into our CMDB, and that'll be step one. So the way we do this is actually using a function that's built into the standard ISC DHCPD server that comes with Linux that allows you to trigger based on certain DHCP events. There aren't a lot of them. There's like 4 events in total. The one that we care about is called commit. And so this is inside the DHCP conf, and what we're saying is on a commit, do all of this stuff. We're setting a couple of variables. Everything in DHCP is this horrible binary format, but there's some built-in stuff to take those binary blobs and convert them into ASCII. We get the client IP, the MAC address, the lease time, and the vendor class, which is a special piece of information that's passed from the client to the server, basically saying, hey, this is what I am. This is the type of hardware I am. And if we have a dynamic DNS name, we grab some value. There's actually a couple of ways this could be set. And we sort of pick from best to worst to try to, and then we execute a script. The one really important thing about this is whatever you run here is completely blocking. It will literally stop your DHCPD server cold. This is a design flaw. It'd be great if somebody went in and fixed it, but as of today, it's basically like a single-threaded C process, and it just stops it. So what we do is run a very, very lightweight shell script that basically just takes a little bit of information, the type of trigger, the client IP, and then off the end of there is also the vendor class. So what type of hardware is this that's talking to us? And we execute it. The trigger script basically looks like this. This is obviously a simplified form, but basically we're just building a JSON endpoint, and then we're running curl, and we're sending a small JSON blob out to another system. And this JSON blob, all it's got in it is the IP, which is the IP address of the remote management console that we just gave it, and its vendor class. And so the other system then is going to make some decisions based on this. One, it's going to say, hey, do I know about this IP address, anything that holds this IP currently? And also, is it something I care about? So we might say, like in our case, we actually only care if it's an iDRAC, which is the Dell remote management card. Anything else we're just going to ignore. Then the next step is to actually inventory the system. So we know there's a system out there that's called into us. We say, hey, we haven't seen this system before. OK. We also actually have its MAC address. And so we're going to go out. We're going to talk to that RMC. And we're going to gather information from it. And then we're going to network boot the system so that we can do things like burn-in tests. So we interrogate the RMC. All systems have basically some sort of serial number. In the case of Dell's, this is usually referred to as the service tag. But using something like DMID code, you can actually ask it for a serial number. And this is a unique hardware identifier. And this is the thing we use in our CMDB to track the life cycle of this hardware forever. And then we determine hardware details. So we query as much information as we can get about it, memory, CPUs, the disks, physical disks that are installed, things along those lines. And then we're going to register all of that information, as I said, into the CMDB for storage. At this point, we know the system exists. So the next step, the system's going to actually boot, basically tell the server to boot. So this introduces one more technology, which is PXE and iPXE. So the Preboot execution environment was a standard that was actually invented by Intel in the 1990s. It's included in pretty much every network card out there today. And it's useful, but it's very dated. It was basically an evolution of BootP and some of the functionality in DHCP. And it uses the trivial file transfer protocol, basically as a way to get media to your system so that it can boot. So you can pass things like an initRD and a kernel image to your system. TFTP is UDP-based, so it's not terribly reliable. It has no authentication whatsoever. It's slow. And it's just something that generally you can't rely on, and especially if you're doing lots of systems, it's really easy to bog it down. So Etherboot was actually started by the open source community, which then evolved to gPXE, which then got renamed to iPXE, and is now called iPXE, which I tell you because it took me forever to figure this out. iPXE is great. It supports a lot of modern TCP protocols, including HTTP, iSCSI, ATA over Ethernet, Fiber Channel over Ethernet, and actually works over Wi-Fi, which PXE does not. It requires a wired connection. iPXE is easily bootable. There's a lot of options of a way to get into an iPXE prompt. You can do it off media. You can actually use PXE to bootstrap it, which is what we'll show in a little while. And if you're incredibly brave, you can burn it to the firmware of your network cards and replace PXE outright. It's scriptable. It supports basic logic within your boot scripts. And it also supports extensions like the syslinux menuing system so that you can actually iPXE into a really beautiful GUI if that's what you need. So the way we chain load from PXE into iPXE is, again, using DHCP. And in this case, this is a basic host example. It's a host definition within DHCP server. We have the Ethernet address of the system, its IP address. When this system makes a DHCP request, it's going to get the normal information, and then it's going to fall into this if-else clause here. And basically, we're checking a particular setting, which is called user class, to see if it happens to be set to gPXE or iPXE. And the first time this runs, when a normal PXE system boots, that will not be set. So it's going to fall down to this last clause that says, hey, file name is undiionly.kpxe. And basically what this is the iPXE boot firmware. So we're going to pass that back. The system's going to boot that, which basically now puts it into the iPXE firmware. The very first thing it's going to do is DHCP again. It's going to send another DHCP request, but this time when it hits this, this user class will be set to iPXE. And this time, you'll see that we're actually passing it a URL and not a file at all anymore. So we say, hey, file name is this URL. And that's going to be passed back to the system. What that file looks like is something along these lines. Now, this is one of the benefits of using iPXE. So you'll see, so basically we have a hash bang at the top. We say, hey, this is an iPXE script. And then we have this colon retry DHCP. Basically, this is sort of like naming a function. It's sort of a label. And then we say, OK, DHCP, and basically grab this next boot file, or go to retry DHCP. So the nice thing, and so what's going to happen is it's going to keep trying the DHCP and grab that boot file forever until it's successful. Most times when you use PXE, PXE just fails, and it fails hard. And then some human, again, has to go and actually touch a button or to actually get the system up and running. In this case, you can actually have your server sit there and wait until you make their boot file available. So you have you can use it for timing to get groups of servers ready to go. And then once that works, it's going to print to the console that, hey, I'm going to go ahead and boot, and then it's going to chain load that file. And then that file is just another small iPXE script. But this looks probably a lot more familiar to people, because basically, it's just a Linux kernel boot line. So we're largely saying, hey, here's the kernel, here's this boot file, the initRD, go ahead and boot the system. And so the first time we do this, we're going to use PXE exactly the way it was intended, which is to network boot a system. We aren't going to install anything on it. We're just going to live boot it. And we're going to get it up and running so that we can do things like firmware updates and ensure that the system's got all the updates that we've decided are appropriate for our systems, as well as doing hardware burn-in. And the important reason to do hardware burn-in is because this is the #1 time when stuff is going to fail very early on in its life cycle. You know, things like hard drives and stuff fail, obviously, over the lifespan of them. But if you're going to discover memory issues, it will usually be very early in the cycle. And so we want to make sure that we test the system pretty hard. These are some of the types of burn-in tools you can use. We don't use all of these, but I have looked at them all. Bonnie++ is great for testing I/O on disks. Memtester is one of the few userland memtesters that you can actually run from within Linux. The Red Hat memtest is just a really simple script, but it does a pretty good job about stressing out the CPU, the memory, and the disk that it's run on. Basically takes the Linux kernel, does a bunch of parallel compression and decompression of it as many times as you want, and will keep the system stressed for as many days as you feel is necessary to feel comfortable with the system. And then this last one is the Phoenix test suite, which is a ton of tests. They're also used for benchmarking. Phoenix does a bunch of benchmark work, and this is what they use to do that. This is an open source suite, though, and it is nice because it's got a lot of very focused tests for things like testing the GPU specifically, or things along those lines. So then finally, we take all the results of the burn-in, and we register this back into our CMDB. So now we've said, hey, the system's good to go, or no, it actually failed a bunch of tests, at which point it'll stop and it'll notify somebody. Assuming that it's passed everything, we finally want to re-PXE boot the system and install it. It's ready to go. It's ready to be used by our developers. So this is when the OS installer, we're going to PXE boot it again. This time we're going to run the OS installer. And again, this is all happening automatically via some APIs and webhooks. And so this kicks off the installer. Depending on whether you use Red Hat or Debian-based distributions, you'll either use something like a Kickstart file or a Preseed file. The difference between these two approach basically is that Kickstart is a really, really small answer file with a lot of sort of free flow scripting capabilities into it, where Preseed tends to be a really huge, deep, complicated sort of answer file with very little scripting capabilities because they expect you to do that in configuration management. You have your package repositories, so this time the installer reaches out, again, based on your distribution, to either Yum or apt to pull down all your packages and get them installed. And then lastly, we do our OS configuration. And depending on where you work, this could be something sort of lightweight, like Cloud Init, or the more heavier configuration management tools like Puppet or Chef. And then finally, we register the results again. We update the host in the CMDB, say, hey, this host is completely ready to go and ready to be handed off. And we have success. We have a bunch of racks, potentially, as many really as your network can handle. But in our case, we did about 120 systems very quickly within a few days. And so we built out this whole system, the CMDB, the source of truth, and then these really small, lightweight processes to push everything through this system. So what are our next steps? Where do we go from here? Well, in New Relic, what I really want to see is us build small microservices everywhere. I want small REST APIs within our infrastructure to sort of go back to the old Unix approach of taking really small tools that are really, really good at what they do and glue them all together. Avoid using the big tools that try to solve all the problems because it makes it really hard to get agile, to remain agile throughout the life of the company. The types of things you might do in here is keeping inventory of the systems, constantly doing updates so that the system itself can report when things change, if disks get pulled out of it, things like system health, being able to do remote configuration, et cetera. And then the future. This is sort of the utopian view, but I would really love to see REST APIs in hardware. I don't understand, as an infrastructure person who's been doing this for 20-some years now, why it's basically the same as it was then. It's painful. Every big vendor who tends to bring in some huge new standard, it's actually just as painful. And it would be really nice to have things like IPMI, things like getting system inventory, talking to the RMCs, all have standardized or semi-standardized REST interfaces. It's not great when you have to write software that needs to interface with SSH on your RMC card. Humans should never be forced to read XML, which is a lot of what the current standards require. And then, of course, we don't want to be writing towards custom protocols as much as possible. And so finally, how might we be able to get there? I'd like to mention the Open Compute project. This is a project that Facebook and Google and some of the really big players in the industry have gotten involved in because even for them, hardware is a problem. They buy lots and lots of it. They'd rather not spend money on it. It's not the thing that makes them money. But of course, they also have to run their infrastructure. They've designed a lot of open hardware with open specs, some network gear as well. They've also are working on writing standardized hardware configuration that, again, is open and available for the community. The one challenge right now is it's Facebook, it's Google, it's a lot of big players. And as a community, I really suggest that people, if they care about hardware and where it's going to end up, get involved in this and make sure that the smaller shops' cares, needs, and desires are also taken into account when this work's being done. So that's it. Thank you very much. And if you have any questions, I'm happy to answer them. Yeah.
I was just curious about what that development process looks like. Like, how iterative was it, and how many servers were actually successful in just on their own, just totally setting it up?
We had some spare hardware while we were designing it, so we probably took about 3 months of iterating over a couple of pieces of hardware, and most of that iteration honestly came from like figuring out the small nuances of the various components. Given that it was hardware, there were a few of them. You know, we dealt with problems like, it turns out the iDRAC 6, which is in our old hardware, and the iDRAC 7 in our new hardware, you know, behave slightly differently, and it was things like that. So it definitely took us a while to get it smoothed out, but once it was smoothed out, usually it's, most of the problems we've seen are sort of between generations of servers, but not so much between individual configurations.
What do you use for your DCI on?
So initially we actually wrote something, and we used that for a little while, and then I actually stumbled across a product it's written by a really small development shop called Device42, which I've been using mostly because it's got a pretty good schema and a good REST API, and I saw absolutely no reason to reinvent the wheel. So, and I haven't found a great open source solution, but I would certainly be open to hearing about one.
How do you map sweep across your new hardware to generate the DHCP, please?
I'm sorry, what was that?
How do you do map sweeping across your new hardware to like generate the DHCP?
So so when they come in the first time and register themselves into the CMDB, when we don't know anything about them, at that point we'll actually create a DHCP record for that DRAC so that we know that it actually exists. You can see the look here.
Are you doing that dynamically though? So are you actually restarting the service every time you add a new record? Or MAC address to the HTTP configuration? Is that something?
Right, like had issues. So we do, but we've got, we actually have like redundant DHCP servers. So we can still respond at any time to a DHCP request, even if we have to restart one of them, we'll just like cycle through them.
But it's just a script that's injecting that into the configuration, or is it dynamically generating?
It's dynamically generating the whole configuration, yeah. Yeah. Sure.
Did you write your own CMDB or?
Well, so initially we did. But so for this project, we actually wrote something that basically just tracked the basic information that we needed to do the job, but we're actually in the process right now of retooling that around this Device42 tool that I was talking about, basically. Yeah.
The Device42 solution can't actually provide everything that you guys had in your original.
Yeah, and more so. And that was the thing, like it can, having done this in the past, you know, going down that rat hole of trying to build it yourself is sort of hard because you can never find that limit about what's the bare minimum you need to know about your hardware. Yeah. Yeah. Okay. Well, great. Thank you very much, everybody.